Welcome to section 16.9. In this section, we will be looking at the divergence theorem, and we'll be looking at a little bit of just kind of a recap of a lot of the work that we've done here in our vector calculus chapter as we bring this whole course to a close. So to start off, we're just going to dive right in with the divergence theorem. So we let E be a simple solid region. So this is one that is simultaneously type 1, 2, and 3. Or in other words, it can be projected onto any of the coordinate planes, the xy, xz, or yz. And let S be the boundary surface of E. Okay, so E is the solid within the surface. The surface is like the outer shell of the solid. Given with positive outward orientation, let F be a vector field whose component functions have continuous partials on an open region that contains E. Then the surface integral of S of F dot ds is equal to the triple integral over E of the divergence of F dv. So we were able to bring triple integrals back in one more time before we get through the end of vector calculus here. Okay, but we have our simple solid region. We can evaluate the vector field over evaluate the surface integral over S of the vector field F, simply by taking the divergence of F and evaluating the triple integral over the solid E. So for our first example here, find the flux of the vector field F is zi plus yj plus xk over the unit sphere. So remember, the flux is just the surface integral of a vector field. So it's just telling us to do this. If we take a look at the divergence of this vector field, we're going to get, so that's partial with respect to x of the first component, plus partial with respect to y of the second, plus partial with respect to z of the third. We get 0, 1, and 0, so that's just 1. We're evaluating the surface integral over the unit sphere. So if we're going to use the divergence theorem here, and you can see why that might be advantageous because the divergence itself is just a constant in this problem. So we need to look at where the unit sphere is. So the unit sphere, S, is the boundary of the unit ball, B, given by x squared plus y squared plus z squared less than or equal to 1. So if we're looking at, sphere of radius 1 here, S is going to be this outer surface, but the ball is everything inside, kind of like inside that shell, right? So E is everything within S, or I guess I called it B. B is everything within S. So using the divergence theorem, we take surface integral of f dot ds. That's equal to triple integral over b of the divergence of f dv. Divergence is just 1 in this case. Now, we could set this up and parameterize, work with spherical coordinates, all that kind of stuff. But when we have the triple integral of a 1, I know it's been a little while since we've talked about something like this, but this gives us a special value, when you take the triple integral of 1, it actually gives us volume. So really, this triple integral is just asking us to find the volume of the ball, the volume of B, which we don't need a triple integral to do. We can just use a geometric formula. That's 4/3 pi r cubed, where the radius is 1. So we end up with just 4 pi over 3. And you absolutely could parameterize, put it in spherical coordinates, set up all of that, but you would end up with the exact same result. In this case, because we had that special relationship of the triple integral of 1, we were able to do it a little bit more simply. Let's look at an example where we actually will be solving a triple integral. So here we have surface integral over S of the vector field F. Okay, and F is this whole ugly mess. And S is the surface of the region E bounded by the parabolic cylinder z equals 1 minus x squared, and the planes z equals 0, y equals 0, and y plus z equals 2. So if we were going to try to evaluate this directly, and I have the surface here so we can visualize why we wouldn't want to do it this way, it would involve 4 different surface integrals, because you would have the surface back here in like the xz plane, that would be S1. You would have the cylinder part itself, so that's everything in here, that would be S2. Everything on the front here would be S3, and everything on the underside down there would be S4. So you would need to evaluate all 4 of those surface integrals and then add the results up together to do this directly. That is not ideal in any circumstances, especially when the vector field contains stuff like this, like e's and sines and all of that kind of stuff. So we want to try to use the divergence theorem to kind of get around this direct calculation if we can. So we're going to set up the divergence of f. So that's going to be partial with respect to x of xy plus partial with respect to y of y squared plus e to the xz squared plus partial with respect to z of sine of xy. And you might already be able to see what's going to happen here. This gives us a y, that first component. With respect to y, this one gives us a 2y. So I'm just going to add that over here. So that's going to be 3y. And then this one has no y's, so it becomes a 0. This has no z's, so it becomes a 0. So the vector field, when evaluating the divergence, becomes much simpler. So even ignoring the fact that we would have to take 4 separate surface integrals, we already have simplified the vector field immensely. Okay. So we're going to use divergence theorem to turn the surface integral into a triple integral. Now you can see here, I've already kind of separated by color the way we would want to do this. In terms of projecting this, it can be projected onto any of the planes because it's simultaneously type 1, type 2, type 3 kind of thing. But there is one that is easier to do because if we project it onto the YZ plane like this, you're going to have half that is in front of the plane and half that's behind the plane, and you're going to have to get the values between 2 halves of the same surface, and that's not ideal. If we project onto the XY plane down here, you'll have this surface going down, but then this one actually cuts into it a bit, so you'd have to draw kind of a boundary here and then evaluate different surfaces for different parts, which again is also not ideal. Whereas if we take this surface and we project it back onto the XZ plane, we end up getting the shape down here. So we're able to evaluate over a pretty simple region in the XZ plane. So this is X and that's Z. So we're going to go ahead and project onto the XZ plane. And for anybody who's trying to keep track of like terminology wise, this is type 3. If you're looking for that type of region. So our surface integral over S becomes triple integral over E. So E is again the solid that's bounded by all of these, of divergence of F dV. Divergence we saw was just 3y. And now to set up the triple integral, the 3D portion is going between the XZ plane, so that would be y equals 0 is that plane, and this surface out here, that's y plus z equals 2, which if we are consistent, that would be y equals 2 minus z for that outer surface. So we're going to do dy with y going from 0 to, 2 minus z. And then for x and z, so this is like the double that gets set up afterwards. We can set this up either way, but there is definitely one better way. That would be to set this up vertically, right? Going from 0 up to this function, and then letting x set the boundaries for the constants. So we're going to do dz dx. Z goes from 0 up to that curve. So 0 to 1 minus x squared. And then x is going from negative 1 to 1. And from here, this evaluates pretty straightforward, because we can pull out the 3, evaluate, we get y squared over 2, plug in the z, evaluate antiderivative, plug in the x's, and then evaluate between the bounds. I will just cut to the chase and tell you we end up getting 184 over 35 for this one. So if you want to get a little extra practice, brush up on your triple integrals, feel free to give that one a try. Make sure that you get the same thing. So, but the divergence theorem itself, all it allowed us to do was to convert the surface integral into a triple integral. Once that work was done, it was up to us to then just set up and solve a triple integral, which is work from, again, a previous chapter. So, but that is the divergence theorem. So the last thing that we're going to take a look at here on the final page, we're going to start looking at the different major theorems that we've talked about in this chapter in vector calculus, and see how they kind of all relate to each other, and see how the main results of this chapter are all higher dimensional versions of the FTC. That is the fundamental theorem of calculus. The fundamental theorem of calculus is right here. This says that the integral from a to b of f prime of x dx is equal to f of b minus f of a, right? Where you're evaluating from a to b, those endpoints, and then the interval in between. Notice in each case that we talk about here, we have an integral of a derivative, quote unquote, okay, over a region. So integral of a derivative over a region on the left-hand side. And on the right-hand side, we involve values of the original function only on the boundary of the region. So for fundamental theorem of calculus, we have the integral of the derivative, literally. And on the right-hand side, we have f of b minus f of a. So this one is from a to b, so it covers the entire region, this whole section. But on the right-hand side, it's only being evaluated at the two endpoints. Now, if we look at some of our other major results here, here's the fundamental theorem of line integrals. We have the line integral of grad f dot dr, so grad f, whose components are the partial derivatives. So this is the integral of a derivative over the curve, so that's the region in question here, is the curve C, equals, on the right-hand side, the original function f evaluated only at the endpoints of the interval, okay, of that curve C. So we can see a little more direct comparison between those two. If we look at Green's theorem says that the double integral over d of partial q respect to x minus partial p respect to y, so this is the double integral of some partial derivatives over the region D, so that's everything in here, equals the line integral over C, that is the boundary only, of p dx plus q dy. Those are the original functions compared to these derivatives. So you can again see a relationship, a link between these. Then we get to today. Stokes' theorem. I've reversed the order to help kind of make this point a little more clearly. Stokes' theorem, we have the surface integral over S, so S is everything in here, of the curl of f. And remember, the curl involves the partial derivatives with respect to x, y, and z. We take a cross product, all that kind of stuff. So an integral of a derivative over the entire region equals the original vector field, not the curl, evaluated over C, which is the boundary curve only around that edge. So again, we see that same pattern popping up. And then the divergence theorem, the one that we just talked about. We have the triple integral over E. So E is the solid. Everything in here is E of the divergence of f, which involves partial derivatives with respect to x, y, and z, equals the surface integral over S. So S is just the boundary surface. It's just the outside edge, the outside shell of f, the original vector field, compared to the divergence of f. So all of these theorems that we have looked at in vector calculus here in this last chapter do all share some kind of core idea, some core relationship, that the evaluation of a region, whether that be an interval, a curve, a 2D region, a 3D surface, or an entire filled-in solid, does have a definitive relationship with the evaluation at the end points, or at the edge, or at the boundary of all of them. And that relationship is more clearly defined using calculus, using derivatives and integrals for all of these in some form. So all of these have a definitive relationship, and they all, perform different tasks. They are all used in different contexts, but they all share some of these same basic ideas. So kind of interesting to see how these are all at least a little bit related to each other as we close out the end of Calc 3, the end of vector calculus. So this is the end of the course. Congratulations on making it through Calcs 1, 2, and 3. That's a major accomplishment. You should be very proud of the work that you have done to get this far throughout your mathematical journey. And this does not just represent the end of this stage of calculus, but a new beginning where you can start branching into other fields of mathematics, start seeing some more uses of calculus, and what lies beyond. We have a lot of tools and skill sets now to be able to use this and apply them elsewhere. So congratulations again on making it through. And that is the last lecture for the course.